Okay, let's do some surface areas. So we're thinking of solids of revolution. Oh, I didn't finish that. Surface areas or solids of revolution. And we're going to draw a picture and see where the formula comes from. It's going to be a similar idea. Let's say we're looking at some curve from A to B. We're rotating this about the x-axis. So what is when we rotate it around the x-axis, right, we get this three-dimensional shape. That looks something like this. And the question is, what's the surface area of this? And as a side note, we're not including this circle part. You could add that if you want. We're just curious about the outside surface area, not the top and the bottom. Okay, so outside. Think of this as being like hollow, okay? Well, we're going to do this the same way we do everything in calculus. Everyone forgets calculus, right? 5 years down the line, you're going to forget most of this stuff, realistically, unless you're using it. If you're using it, that's great. But if you remember nothing else about calculus, I want you to remember this concept that we've been doing all through Calc 2, really, is that Calc 2 and really calculus in general, right, is just doing a bunch of things on an infinitesimal scale. So again, we're just going to take this into tiny pieces, add them all up, and take the limit, essentially. So that's basically what Calc 2 is, all right? So again, let's just look at little pieces. We can approximate each of these with lines. Why are we doing lines instead of just approximating with rectangles like we did before? The reason why approximating with rectangles is not useful is for arc length and surface area, we care about not just the x's, but also the y's, right? We're looking at this diagonal distance. So if we only do the x distance, then we're missing out on this y change as well. And for surface area, we need that whole surface. Yeah, we just approximate this with a bunch, right? With a bunch of lines. And then we rotate each one of these around an axis. So let's just look at, oh, that was a bad line. So let's just look at one of these and see what it looks like. If we just look at one of these, we have what's called a frustum. Okay, I'm going to draw this picture for you. Again, let's just enhance, just like those shows, right? If we enhance this picture, we have this sort of solid, which is just kind of like part of a cone, right? If you want, right? It's just like if someone chopped off the end of a cone, but it's basically a cone. And there's a lot of geometry you can do to find the surface area of this cone. The book has it all. I do not want to spend 10 minutes doing geometry right now, so I'm just going to tell you the area of this cone. The surface area of the outside of this cone. So just again, we're not looking at the tops or the bottom, we're just looking at the outside of the cone. So in fact, maybe I will just really emphasize that by shading in this region here. We're adding up all those regions on both sides, but we're not adding this top or bottom. So if this top of the cone has radius, let's use a different color, make it a little easier. If this is some radius, and this is, again, they're both circles, this is some other radius. And then this guy right here, let's actually do it on the bottom, is some length of L. Then we know that the area of a frustum, I only hear that word in calc classes. I've never heard this word anywhere else. Who talks about frustums? If you know the word frustum, tell me. I'll get really excited. So the surface area of this frustum, I have to check my notes because I don't remember it, is pi times the radius, the radii added together. Or basically it's pi over, it's 2 pi times the average times L. Okay, which is actually similar to the area of a parallelogram, because this is kind of like the Kind of like the circle version of a parallelogram, but in 3 dimensions. So I guess that kind of makes sense. And then you could like unwrap it, unfold it, and you get a parallelogram. Actually, you unfolded this, you would get exactly a parallel. That's where it comes from. Okay, that's the surface area of a frustum. So now let's think about this in terms of calculus. All right, I'm getting excited. Jacket's coming off. Think of this in terms of calculus as these intervals get really, really small. So as our delta x gets really small, as our partition gets infinitely fine, what are these quantities looking like? Because we want to add up infinitely many of these, right? That's what our goal is. Our goal is to add these all up. As this horizontal distance gets smaller and smaller and smaller, well, as this chunk, right, gets thinner and thinner and thinner, well, we can think of this R1 as the function value, right? In fact, both of these R's are the function value. R1 is the function value at the start. R2 is the function value at the second one. We could call this f evaluated at some x sub I. And the second one is also going to be a function value, but delta x later. And remember, delta x is getting really, really small. So as delta x is going to 0, as these are getting thinner and thinner, these become the same thing because our function's continuous. Okay? So this essentially is becoming, this first part is becoming, let's do it on the next page. This first part is just becoming 2 f of x. As delta x goes to 0. What is L becoming? Well, L is this distance. Oh, L is that arc length. We could draw another triangle, right? Draw another triangle, delta x, delta y. We already did the work. We know the arc length of the, oh, that's why this is in 2.4, right? Because this L is arc length. And what's arc length? Square root of 1 plus y prime, or yeah, y prime times dx. So if we add all these up, what we get is that the surface area becomes the integral from a to b of pi times 2 times f of x times the arc length component, 1 plus f prime of x squared dx. And that's how we're going to find surface areas. We usually rewrite this a little bit, right? We can take the 2 pi in front. That's where it's all coming from. All right, that's the one part. That's the other part. We add them all up, get that integral. So we get surface area. And let's start by rotated about the x-axis. It's going to be kind of like the disk method in the sense that if it's rotated around the x-axis, we'll just take out the 2 pi. Rotated about the x-axis, we'll have things in terms of x. We're just copying down that formula and cleaning it up a bit. And then if it's rotated about the y-axis, it's very, very similar. Okay. Whoa, it's not that similar. I literally wrote x. I meant y this time. Well, it's going to be 2 pi integral from c to d of f of y times the square root of 1 plus. Again, everything holds the same. Choosing y's instead of, it's the same formula. The important thing is that this is the surface solid of revolution under f, and the second one is a solid of revolution to the left of f. Okay, we'll see that in this example problem that I'm about to do. But that is an important distinction. Okay, otherwise they're basically the same formula. Just remember that when we're talking about things in terms of y, we're thinking of left and right. Whereas in terms of x, we're thinking of up and down, top and bottom. Let's do an example in the next video. This video is over. I'm trying not to have 20-minute videos, so I'm getting excited. You're going to have to press play on the next one to see an example. But it's basically plug and play. Good luck. Bye-bye.